Welcome everybody to the last magnetism video. We've made it this far, and while we have glossed over many things and cut a lot of stuff out considering our current learning conditions, and we've cut a lot of demos out unfortunately, this is something that we can't skip over because it's in the end the main reason we study magnetism. So in our previous videos, we saw that moving charges create magnetic fields. A straight wire creates a circular field, and a circular wire creates a straight magnetic field. But either way, moving charges create magnetic fields. I wonder what would happen if we had a moving magnetic field near a wire. Say it in reverse. Moving charges create magnetic fields. Moving magnets can induce currents in wires. I realize that this is recording at 15 frames per second, so you may not be able to see it. But if I take this magnet and I move it near this coiled wire, you can see the little compass needles are changing direction. When this happens, we are inducing a current in the wire. So what you want to take away from this is that when you have a changing magnetic field near a wire, electrons will move. That's basically it. Moving or changing magnetic fields induce a current in a wire. So that's where generators come in. What if we could constantly change the magnetic field near a loop of wire? So I'm going to make this bigger. Hopefully it has a better effect. Big wire. And we have the maximum. Okay. So basically this is your standard generator. In a real hydroelectric dam, they have large turbines that spin magnets near coils of wire. So this coil of wire here on the right is stationary, but if we get some water flowing, we can have a constantly changing magnetic field near this coiled wire. That causes the electrons inside to move. Again, a changing magnetic field near these electrons causes the electrons to move. And again, I am simplifying this. Trust me, there is a right-hand rule to go with this. There is math to go with this, but considering the circumstances we're in now, we want to focus on the basics, which is a changing magnetic field near a loop of wire induces a current. And you can see how the compass needles in and around the loop of wire are constantly changing. What I'm not sure you can see, because of the 15 frames per second, is that the direction of the current is changing back and forth. I've used the voltage meter so you can see this. So it's going positive, then negative, positive, then negative. This is called alternating current because it alternates directions. So basically, we need to get this power to your house because we're generating electricity, but with it, we need to get it to your house. And again, this is why we study magnetism. Without magnets, you have no electricity. So we have to suffer through this together, and that's why we're doing it. So that's where the transformer comes in. Here's a transformer, or what would be the beginnings of a transformer. On the left, we have our electromagnet, which we saw from the previous video, that a loop of wire creates a straight magnetic field. This is direct current. It's flowing in one direction. So as you can see, the magnetic field compass needles aren't changing. However, we can make it AC. So now that current that was created by the generator is sent to this loop of wire. And if you focus in on the compass needles, they are changing back and forth. So this coiled wire on the left that I keep moving around, when it's near the stationary coil, it's inducing a current in it. Again, the smaller wire here on the left, the current's going back and forth, creating a changing magnetic field. The wire on the right is like, hey, there's a changing magnetic field. I'm going to induce some current. And that's basically what happens. And I don't know how well it is in this 15 frames per second video, but you should be able to see, hopefully, that the changes in current or the movement of the current is opposite in each wire. But basically, this is how a transformer works. So we've gone from generator to transformer to getting that power to your home. So let's talk about the transformer a little bit more, and we'll talk about how that power gets to your home. So this is a picture of a transformer. We have them at school, and we would demo this and use all the equipment so you could really see it happen, but we're not at school, so we're going to do the best we can. But basically, you have a primary and secondary side. and the current will come in on the primary. I'm making this blue current, and it'll wrap itself around through this coiled wire. Now, if we use the right-hand rule for a coiled wire, our fingers are kind of going to the right and around, which means your thumb should be pointing up. So it creates a magnetic field that goes up, over, around, and back in. I mean, it's everywhere, but I'm focusing on one magnetic field line. But this is alternating current. So then the current changes direction, and now we'll make it go to the left. Now my fingers kind of go left and around. I know I'm talking and modeling and you can't see me do it, but I'm doing my best. And your thumb should be pointing down. Now, all of a sudden, the magnetic field has changed direction. So as the current goes from blue to green, it creates an alternating magnetic field, blue and green. The secondary wire is like, hey, there's an alternating magnetic field. Let's induce a current. That's the primary concept here, no pun intended, is that a changing magnetic field near a loop of wire will induce a current. So to put that in not so many words, here you go. I apologize for the sloppiness of the writing, but basically saying what I just said, an alternating current on the primary creates an alternating magnetic field, which is felt by the secondary. This alternating field induces a current in the secondary. Again, any changing magnetic field near a loop of wire will induce a current inside it. That's basically how a transformer works. You've seen these transformers. They are outside on power lines, on the telephone poles. They're the cylindrical objects. Inside is actually, it's not the rectangular one here, which is an iron bar, which is very magnetic, and has magnetic properties. It's usually one coil inside the other. And I mean, that's just semantics. We would have done this as a demo at school, so you can actually see this work. But the mathematics to go with this are actually pretty easy. So here we go with that. You can't have more power on one side of this transformer than you do on the other. It's just physically not possible. Where does that extra power come from? So the statement starts with that the power on the primary must be the power on the secondary. They have to be equal. You can't have more. Where's that power coming from? So this is in terms of current and voltage, because technically the changing field doesn't induce a current, it creates a voltage, and that voltage pushes the current. But again, we are simplifying this for obvious reasons. So what I can write here is that the current on the primary times the voltage on the primary is equal to current secondary voltage secondary. That's our expression for one of our expressions for power, which is current times voltage. If I rearrange these things, I get that the voltage on the primary over the voltage on the secondary equals I secondary over I primary. So there's this relationship, and you can see that the S's and the P's are inverse, they're switched, which makes sense, because if the voltage goes up, the current must go down to keep both sides of the equation the same. So there's another part of this equation which we would derive from other math, which we don't have, but it's NP over NS. And this is actually the transformer equation. Now, N is the number of loops or coils inside, either on the primary or the secondary. That's the number of loops, and voltage is voltage, current is current. So here's an example of how to use this. We'll do some easy math. And let's go with the little purple here. All right, so this side has 4 turns. The primary side has 4 turns. The secondary has 8. I drew it like that on purpose. And let's just say that the left side has a voltage of, what's an easy math? 500 volts. How about that? Okay, well, what's the voltage on the secondary? This is very easy math. Number of turns on the primary, 4. Number of turns on the secondary, 8. Voltage on the primary, 500 volts. Voltage on the secondary, this is pretty easy math, but you should be able to get that the voltage of the secondary is 1,000. So the voltage has actually gone up. And oops, I didn't mean to write amps. The voltage on the secondary has gone up. And we're going to talk about that in a second. So we now know the voltage on the secondary is 1,000 volts. What about the current? What can we do with that? Well, the current, I'm making up numbers. Let's just go with 50 amps here. What is the current on the secondary? All right, do a little math. Now you can use either number of turns or voltage. You can use number of turns or voltage. Totally up to you since you now have both voltages. I'm going to use the number of turns though. So it's a 4:8 ratio, primary to secondary. Be aware that the secondary to primary on the current, it's flipped. So the secondary goes on top in the numerator, and this is 50 amps down here. And you'll notice that the current on the secondary is 25 amps. If you were to multiply voltage times current on each one, either way, you're going to get 25,000 watts. So we've kept the power constant. So we need to talk about this. There is something called a step-up transformer. Step up. Basically, in that scenario, the number of turns on the secondary is greater than the number of turns on the primary. That also means that the voltage on the secondary will be greater than the voltage on the primary. Now, this is the big deal here. Step up means stepping up the voltage. So the step up is really the secondary voltage is larger, but that also means the secondary current must be smaller to keep, excuse me, to keep the power constant. Step down would be the opposite, where the number of turns on the secondary is less than the primary. The voltage on the secondary will be less than the voltage on the primary, but the current will increase. So these are stepped up and step up transformers. There's usually a homework to go with this, but again, we are trying to slice and dice this unit and only cover the important stuff. So this is the equation. We're going to use it a little bit in a practice problem right about now. But in the grand scheme of things, you should just remember step up versus step down and what it means in terms of voltage, because that's what it's about. So we're about to venture off into doing the notorious problem about getting power to your house in that process. So here we go. So this is the problem we normally do in class as an example. I want to stress that this is a very simplified, a super simplified version of how the power gets to your house. I'm going to set this problem up. There's going to be some things I'm going to write down, but eventually erase a little bit. But the point is, when we study magnetism, without magnetism, you would not have electricity. And now we have to talk about how that electricity gets to your house through the use of transformers, which also work on magnetic principles. So that's why we really study this topic. It's important. So we're going to read the problem, and there's a drawing here to go with the problem that you're going to fill in. Please trust me, filling in and following this method in normal times, people love this problem on our assessment because you just follow a process and you do great. If you don't follow the process, you're lost. Follow the process. So we're going to read some things here. We have a 100 megawatt AC generator producing 12 kilovolts. You may want to write this somewhere else on the side, but megawatt means 10 to the 6th. Mega means 10 to the 6th. Mega millions is a good way to remember it. It means millions. So 10 to the 6th. And you should know by this time of the year that kilovolt or kilo anything is 10 to the 3rd. So don't write this on the in-class example. Put it off somewhere onto the side. But you're going to need to know that because, well, you need to know that. So I'm going to erase it. Here we go. You just got to remember that mega means 10 to the 6th. Kilo means 10 to the negative 3. Let's read this. This says that there's a 100 megawatt AC generator producing 12 kilovolts of voltage. So my generator is this weird symbol on the left of our picture. So I'm going to write 100 times 10 to the 6th watts, because that's what it's producing. And it's producing 12,000 volts, or 12 times 10 to the 3 volts. Terrific. This is sent through a certain type of wire to a transformer that's 100 meters away. So the easy thing here is that the transformer is 100 meters away. Well, I'm going to fill that in my picture. The length of this wire is 100 meters. And here is my transformer right there. I know it doesn't look like the one I just drew, but that is how we're going to be drawing a transformer for now. So the 1000 MCM wire. The chart on the right here has, it's AWG, which is American wire gauge. It is a standard gauge of wires. All we really care about in this picture is the stuff on the right. So it says 1000 MCM wire. That's nice. Look at the chart, not at me changing the colors here, but look at the chart, find 1000 MCM wire. I find it right here on the bottom. And it says the area is 500 millimeters squared. As you know, we don't like millimeters. We have to convert to meters by dividing by 1,000. Except that it's area of this wire, so it's squared, which means we have to divide by 1,000 twice, or 10 to the negative 3 twice, or 10 to the negative 6. So the area of this wire is actually 500 times 10 to the negative 6 meters squared. I'm going to write that right here. 500 times 10 to the negative 6 meters squared. Literally, all I did was tack on a 10 to the negative 6 to that number. No big deal. It then says, as I continue to go back to the problem, that this electricity is sent to the transformer that has a turn ratio of 1 to 40. So I'm going to write that right on my chart. 1 to 40, right on the picture. This is definitely a step up transformer because there's more turns on the secondary. It says afterwards that this electricity, this power is sent through 2,000 kilometers. So that's the length of 2,000 times 10 to the third, or 2 million meters, a lot of meters, through a wire that has a 500 MCM wire. So we go to our wire gauge chart, we find 500, and we look and we see the area is 240. So the area of this wire is 240 times 10 to the negative 6 meters squared. It says it then reaches a substation where it is stepped down to 240 volts. So we know the voltage. I'm going to put 240 volts here. We don't know a turn ratio. We know the voltage. From here, excuse me, we want to figure out how many homes can be powered if each one gets 200 amps. Now, there is a specific problem-solving process for this. And I'll review it at the end of this rather long video. But please, just follow these steps. It's kind of mindless, but I really need you to know that transformers are essential to getting power to your house, and we have alternating current. So here we go. So my chart is completely filled in, and I'm ready to figure everything out. There is a process. Here we go. The first thing you want to do is figure out how much current is being produced, because we know the voltage and the power, so what is the current? So I can use I equals P over V, which would be 100 times 10 to the 6th watts divided by 12,000 volts, and I'll get that the current that is produced is 8,333 amps. Terrific. So this thing is producing 8,333 amps, and we now need to ship that current to that transformer, which is 100 meters away. The problem is that wires have resistance, and we lose power that way. And this is 100 meters of wire, so it's definitely got some resistance. We need to calculate that. I'm going to bring back one of our old friends from circuits, which is R equals rho L over A. I want to stress that we're going to be using copper, and the resistivity, the rho, is going to be 1.68 times 10 to the negative 8 ohm meters every single time. The length is 100 meters, and the area is 500 times 10 to the negative 6 meters squared. It's not a coincidence that in my diagram, I put L on the top and A on the bottom. From here, we're going to get that the resistance, it isn't much. It's 0.00336 ohms. It's not a lot. That's an ohm symbol, sorry. Now we have to figure out how much power we lose. So that's our power lost. Our power lost, we're going to do I squared R, which in this case is 8333 amps, times the resistance, 0.00336. Now, again, not a coincidence. Step 1, we found the current. Step 2, we found the resistance. Step 3, we put them together, and we find that the power lost isn't much, but it's about 233,314 watts. So how much power do we have remaining? That's your last step, P remaining. Well, we started with 100 million volts, 100 million watts, and we just lost 233,314 watts, and we are left with a total of 99,766,686 watts. Now, some people take that as soon as they get that number and they write that up in the middle here, which you are welcome to do. I'm writing it, sneaking it in there. You don't need to, but some people like to know that's how much power we're starting with. Okay, and also notice how I tried my best to do all my work right underneath that first section of our distribution of power. So now we got to start the whole process over again. Here we go. And the first thing we're going to find is the current. Yay! In this case, we were given a turn ratio for the transformer. That means we need to use the transformer equation. And that'll be NP over NS equals IS over IP. From here, the turn ratio is a 1:40 turn ratio. Current on the secondary we don't know, but the current on the primary is 8333 amps. This gives a current on the secondary of, I think it's 208.3. So notice that we have stepped the current lower, but the voltage will be going up. It's 40 times larger. So the original voltage was around 12,000. That means the new voltage is almost 500,000 volts. That's why those high tension wires and those big towers say high voltage, keep off. Yeah, because they're like easily in the millions of volts. You don't want to be around that. Step 2, we need to find the resistance, always. So R equals rho L over A. That's going to be 1.68 times 10 to the negative 8 ohm meters. The length, I just look up at my diagram, I see 2 million meters. All over A, which I look up in purple, and I see 240 times 10 to the negative 6 meters squared, and I find out that the resistance of this wire is 140 ohms. Next step, how much power is lost? It's going to be I squared R every time, I promise. That's why we found I first, then R. That's going to be 208.3 amps squared times R, which is $1.40, giving us a power lost of a lot. It gives us 6,074,444 watts. That's a lot. Now, I want to stress this. Without transformers, if we still had 8333 amps of current, well, if you do 8333 squared times 140, I think it's over 100 million watts lost, meaning you've lost more than the power you started with, and now you have negative power. That makes no sense. The point of that means you can't ship current and power over large distances without a transformer. That's why we study this. The transformer helps to make the voltage go higher so the current goes lower and we don't lose energy while shipping power. Speaking of power, how much we got left? That's always step 4. Step 4, power remaining, P remain. And that's going to be the power that we started with, which you can either look to the left here or maybe you wrote it up on the top. That's going to be 99,766, 686 minus the power that we just lost, which is 6,074,444, and that gives us a power remaining of, I did not want to do that, sorry, 93,692,242 watts. So again, some people like to write that right away up top. I will. 93, 692, 242. All right. We're almost there, people. Your troopers are staying with it. So I'm going to cut off the second part of this problem. Sorry, I'm having tough time putting this all organized on such a small area. All right, guess what we're doing? We're finding the current. And we don't have a turn ratio, but we do know the power and the voltage. So again, we're going to be doing I equals P over V. The reason I know to use this, again, is I know the power in red and the voltage in blue here. So that is simply going to be 93, 692, 242 watts divided by 240 volts, giving us a current of about 84 amps. We need to ship this current 200 amps per home. So you do the math, divide by 200 amps per home, and we find out that you can power approximately 1,951.9 homes. So this step down transformer, the 240, that's usually the one that's on the telephone pole. But the substation up here, the substation area, those you can see, well, I think there's one on Terrell Road, I believe it is, or it might be on Martine, where there's just like a lot, it's like a parking lot with a lot of electrical stuff and it's fenced off. That's a substation that's usually stepping down the voltage and stepping up the current before shipping it out on the telephone lines or telephone wires to your house, where it's finally stepped down to 240 volts and the current is increased. Now, if you want to find the percentage of power lost, I will show you how to do that when we get to the next screen. But before we do that, I want to just review really quick the problem-solving process for this. The first thing you want to do is read the problem and fill in the diagram. That's like, definitely got to do that. Fill in that diagram. Label the powers, the voltages, the lengths, and the areas. After that, the process is always the same. So the first thing you're going to do after you do that is you're going to get the current. So how much current is there? You have two choices. You could do I equals P over V. When do you use that? Well, when you have the power and the voltage. Or you can use number of turns on the primary, secondary, current secondary, current primary. You use a transformer equation. When do you use that? If they give you the number of turns on the transformer. It's that simple. If you filled in your chart, you'll know when you use the turns versus the power or the voltage. Step 2, always, what is the resistance? And it's always going to be resistance equals rho L over A. Again, strongly suggest you put the L on and the A in your diagram so that it's just L over A the way I modeled it in the problem I did. Remember, the A is going to be times 10 to the negative 6, and rho is always going to be 1.68 times 10 to the negative 8 ohm meters. Step 3, how much power is lost on each step of getting power to your house? That's always going to be P equals I squared R. And step 4 will be the power remaining. And that's it, which is obviously the power you started with minus the power lost, and that'll be your new power for the next part of the problem. In terms of percent of power lost, going back to the previous problem, that's pretty simple. You started with 100 million watts. We lost we ended up with 93,692,242 watts over how much we started with, which is 100 million. This is actually pretty easy because of the 100 here. Oops, why did I put a 1 there? And you'll get that the power percent lost, I guess, is simply percent lost is just going to be about 6.3% lost. So that's it. I realize that this was a rather long video and it's a lengthy problem to complete and it's monotonous, but I really need you to understand that the reason we study magnetism is that changing magnetic fields induce currents in wire, and that's how we get our power. And without transformers and the magnetic properties that they have, we would never get that power to our house because we lose all the energy and in the wires because they would heat up and the I squared R would be through the roof. So if you need me for anything, please email me or see me during office hours. I realize these problems can be tedious. You're more than welcome to work with somebody else on this problem to make sure you're getting the same thing, because one math error screws up this entire problem. But I wish you the best of luck. I hope you're all well and you take care of yourselves.